All right, so your marks have been up online. I think you've had a chance to take a look at that. Tomorrow I'll be handing out your interim reports, which will go home in preparation for Parents' Night on Thursday. Now we continue on to the second unit in this course, and it's on light and optics. And it's kind of a neat unit. It's very hands-on in that we're not dealing so much with chemicals and maybe the unknowns of what happens in a chemical reaction, because sometimes a chemical reaction can kind of almost be like magic in that we can't see the atoms and we can't see the ions and we can't see them getting together, but we can see the results of the chemical reaction. So it's kind of neat. We put something in and a new color appears. And it's, like I said, it's almost like magic. Light and optics is less kind of, magical in that we can see the beams of light that we want to deal with. We can see what's happening to the way something reflects or how light interacts with a substance. So therefore, it's a little less kind of magical, which maybe is maybe not as cool, but it's easier to understand perhaps. So this unit is broken down probably into three different main groupings. The first part we're going to deal with is what light is. What is light and how do we make light? And then an introduction to the way light moves and what it does. And then the second part of this unit deals with what happens when light bounces off of a substance, and we call that reflection. So we're going to talk about, hold on, I got troubles in the world. I got a movie playing in the background. Doo-doo-doo-doo. What is happening here? Oh, right there. That movie is running. And I think we're still good to go. I'll bring this back up. Okay, it's good. No, we got it this here. Where's my PowerPoint? Nope. Excellent. I could hear myself talking through the Bluetooth. Okay, I've stopped talking. What did I say? Oh yeah. First part of the unit is going to be on what light is and how it behaves. Just in essence, the way light behaves. Second part deals with what happens when light encounters an object, when it bounces off of something, and that's called reflection. And we'll talk about how various types of mirrors can be used to control where light goes. The third part of this unit deals with what happens when light goes through a transparent substance, such as glass or water or even air itself. Air is a transparent substance that light can travel through. So we want to talk about what happens under those conditions. So that's really the three main parts of this unit. So for today, we want to talk about what light is. So what is light? And you can write that down because I am going to explain in a moment what light is. Before we write down what it is, I want to talk a little bit about the origins of the ideas of what light is. Obviously, light is an important thing for us in that, the fact that we have artificial light allows us to, work beyond the day's hours. When the sun goes down, we can continue to do things because we have the ability to produce light. And so this need to have light in order to do things has really made the subject of what light is kind of a very important thing. The Greeks had ideas of what light was. The Greeks believed that light originated from the eye itself. It was kind of a crazy idea. But when you opened your eyes, you could obviously see the light. And when you closed your eyes, you couldn't see the light. And so therefore, maybe the eyes themselves were in charge of giving off light so that something could see. That's a crazy idea. But, that's an origin or an idea of what light was. There were two competing theories for what light was. Sir Isaac Newton had a theory, and his theory was what we would call a corpuscular theory. He believed that light was made up of little pieces or particles, like, little pieces of sand or something that were coming out of this object that produced the light. The reason Newton thought that light was made up of little pieces or particles was because Newton had laws of motion that dealt with how things moved. And so he was very good at explaining the way an object, like a little particle, whether it be a stone or a ball or a cart back then, in the 1700s, he had theories on why and the way objects moved. So it was only kind of logical for him to extend the idea of light as being made up of a bunch of tiny little particles, all right? He even had gravity affecting the way light would move. Again, one of his big theories was gravity. So if he imagined the light as being made up of little particles or little pieces, he could use then gravity to explain the way things behaved. He even explained different colors using different sized particles. He believed that our eyes perceive different colors based on the size of the particles. So that's what we would call a corpuscular theory, in that a corpuscle is a tiny little piece or something, all right? About the same time, there was another scientist by the name of Christian Huygens, and he had what we call the wave theory of light. He believed that light was made up of waves, and that if you believed and analyzed light as being waves, you could explain all kinds of things that light and waves do, right? Light can reflect off of a surface, right? Now, a ball can reflect off of a surface if you throw a ball at it, and a wave can also reflect off of a surface, right? Sound waves can reflect off of walls, and even if you have water waves, if you've ever stood at not necessarily at the beach, because the beach isn't very good at reflecting waves, but if you've ever been to maybe a lock, you know what I mean, the locks where the boats go to rise up and down, that type of thing, they've got the big concrete walls. If you ever carefully watch the waves, they'll literally bounce right off of the wall and they'll head on, in the other direction. So waves can reflect, light can reflect, but then also particles can reflect. So there was this battle kind of for whether light is a wave or light is a particle, right? So all kinds of things that we see light do, particles can explain them and waves can explain them. So for many years, there was a battle between the scientists. Is light a wave or is light a particle? In the early 1800s, a scientist by the name of Thomas Young did an experiment called the double slit experiment. And I can't go into detail on the way the double slit experiment works because you need to know a lot more about waves and the way they behave. But if you take grade 12 university physics with Mr. Petrus, in that course, they talk in great detail about the double slit experiment. And this experiment was kind of the final bit of evidence that allowed the wave theory of light to kind of win in terms of explanations. So we now believe that light is a wave and not made up of little pieces. So if we think that light is a wave, the next question was, what is waving? What is doing the waving if light is a wave? If we have a water wave, obviously water's bobbing up and down. If we've got like a rope or a garden hose, and you flick the garden hose and the wave goes down to the end, the garden hose is doing the waving. So the question for light is, what is doing the waving, all right? A scientist by the name of Maxwell, James Clerk Maxwell, had an idea on what was doing the waving, and I'm going to guide you through an idea before I tell you what is doing the waving, all right? So let me just show you something here for a moment. And I'm going to write some of this stuff down that I'm talking about on this whiteboard paper here so that those who are watching the video can write it down too. So what I have here in front here is a pith ball, right? Pith ball hanging from a string. And in grade 9, you've seen the pith balls. You can take the ebonite rod and you can take the rabbit's fur and you could rub the ebonite rod and you can get it to be charged. And I believe this is a negative charge. I don't know if you remember from last year, but the ebonite rod results in a negative charge. And if I bring it close to the pith ball, I can transfer some of that charge to it. And it's really not a very strong charge, so I'm not transferring much, but I'm hoping that I can make that particular pith ball negative. Now what I'm going to do is I'm going to take this plastic rod and I'm going to rub it with this plastic bag. And when you rub the plastic rod with a plastic bag, you end up with a very strong positive charge. And you can see here that I can cause that thing to attract. That's fun. Ooh, I don't want to touch. And that's just good fun stuff. Oh, I obviously made some contact and transferred some positive charge, so now it's repelling. But I can get that pith ball to move, and we know that to be some laws of electrostatics. Does that sound familiar to everybody? All right. So I'm going to cause this thing to charge up again. I want it to be a negative charge. And now I'm going to get you to think about a little experiment, and I'm going to write this down on the screen, and you can write this down as well. Let's imagine then that I have the charged ebonite rod, and I'm going to let that charged ebonite rod be represented by a sphere, right? There's the ebonite rod, and I'm going to have this be positive, all right? And I do want you to write this down, please. And I'm going to put the pith ball over here, and I'm going to change the pith ball a little bit in that I want you to imagine that the pith ball has a hole in it, all right? So that's the pith ball, and I put like 2 little circles there to represent it's got a hole in it. And let's imagine that that pith ball is then attached to a rod. So I'm going to just put that rod all the way up through there. So the pith ball is attached to the rod, and the pith ball is able to move up and down the rod. Is everybody kind of visualizing this? It's able to move freely. And let's say that I took a rod and I charged this pith ball to be negative, and I have the other rod there, just like I did there, and it is positive, okay? And now, and in this case, I wonder if I can simulate it in real. There, see how it's attracting still, so it must be negative. So I've got this situation right here. Everybody kind of see what I've got here? The positive and the negative, the positive and the negative, okay? So here's the question. I'm going to take the positive rod and I'm going to move it. I'm going to wiggle it. I'm actually just going to, in this case, I'm going to wiggle it back and forth, but in my simulation, I'm going to move it up and then I'm going to move it down. And the question is, what's that pith ball going to do? What's the pith ball going to do if I take this positively charged rod and I move it up and I move it down and I've got a negative pith ball that's on a rod there, free to move? What's going to happen to that pith ball? We call this a thought experiment because we're just thinking about it. We're using what we know about electrostatics. Prediction. What's going to happen? Yep? Yeah, the pith ball will follow the path. When I move the positive one up, the pith ball should move up because it's attracted to it, right? Opposite charges attract. And when I move the rod down, the pith ball should move down. Now here's the real question. When I move that up, does the pith ball move simultaneously as it moves up? Or is there a delay between the moving of the rod and the moving of the pith ball? Simultaneous or delay? What do you think? Megan's making all kinds of facial expressions here. She's going, no, yes. What do you think, Megan? You think it'll delay? The answer to the question is yes. There is a delay, all right? It doesn't move simultaneously with it. It's as if you move the one up and then the other one moves up. Now let me explain why there's a delay. In electrostatics, and that's what this study is, a scientist by the name of Michael Faraday wanted to understand why something like a negative pith ball was attracted to a positively charged rod. So he invented something that we call the electric field. And this is a picture, a representation of the lines of force that can exist around something like a charged rod. So the electric field for this particular pith ball would emanate away from the pith ball as if it had all these different lines of force that were attracting this negative rod to it. And these lines of force actually have a direction. In this case, they're away, all right? So we call this thing the electric field. And all objects that are electrified exert an electric field. The Earth exerts a gravitational field. We feel the force of gravity because we are in Earth's gravitational field. An electrically charged object exerts an electric field. And it virtually connects itself to other electrical charges. Now, when you move the rod up and down, if I take this rod and I move it up and then I move it back down, what that does is it puts a little bump in the electric field. It puts a little wiggle in the electric field that surrounds that thing. So, if I've got my negatively charged rod here, and I've got my positively charged rod here, you can see that there's that attraction. And if I wiggle it back and forth, you can see there, isn't that fun? It's almost like magic. I can get that pith ball to wiggle back and forth. As long as I do it properly, I can get it to wiggle back and forth. I can get that wiggle to be pretty large. Around this rod, there's an electric field. It's pointing off just like rays of a sun that you drew when you were like 4 years old. Everybody know how to draw the rays in a sun, right? If I wiggle that, it causes a bump in the electric field and it travels away from it. All right? You can't see it, because you can't see the electric field. But I just did it. See? See that? This thing can feel it because it feels electric fields, and it can feel the bump in the electric field. Mr. Maxwell, when he did the mathematics to figure out what light was, right there, that's light. When you have an electric field and it accelerates, what do I mean by accelerates? What does it mean for something to accelerate? Anybody know that term? What does accelerate mean? Any ideas? Grow, yep, kind of. Any ideas? Accelerate? No? In terms of physics, accelerate means to speed up, which would be to get bigger, right? Or slow down, or change direction. That's what an acceleration is in physics. So when a charged object speeds up, slows down, or changes direction, really anything that wiggles is accelerating because it's got to speed up, stop, turn around, come back, stop, turn around, come back. An electric charge that accelerates produces light. So Mr. Maxwell stated that when you have a wiggling charge that's accelerating, you're producing light. Now, what receives light? Anything that's a charged object that can sense that wiggle in the electric field is a light receiver. It's a thing that can sense that light. Now, you guys aren't buying anything in terms of this light business, because I'm telling you here that if I wiggle this rod, I'm producing light, and that's the light receiver. And I'm going like this, and I'm saying, see the light? Can you see it, Allison? See the light coming from it? And you're all going, Mr. Sanders must have had a crazy weekend because he's lost his mind. This is light, but it's not visible light. We're going to learn today there are many different types of light, and some light we can see, and other types of light we can't see. This is of no use. The only use this light can do is wiggle a pith ball. That's maybe fun for a party maybe once in a while, but other than that, it's of no fun. If you wanted to see this light as visible light, I would have to wiggle that thing up and down at a frequency of 10 to the 14 times. We all know scientific notation. 10 to the 14 has like a lot of zeros on it, right? So I'd have to wiggle this thing up and down 10 to the 14 times each second. And if I could do that, then it would start to produce visible light. With glow on the end, I can't do that. That'd be awesome if it did, right? I contend that Hogwarts is not a school for magic. It's a school for physicists, right? And the end of the rods are all charged, and if they wiggle it fast enough, they say, Lumos. That's all they're doing. What's that? Now, obviously I can't actually make that happen, but there are things that produce visible light, like the lights, right? The lights are producing visible light. It's the electrons in the atoms that make up the light that are jumping up and down from one orbit to another. Remember our orbits? I taught you in chemistry that they sit in their orbits. The electrons can actually jump to higher orbits and fall back down. When they jump up and down, they wiggle very fast, and they produce visible light. In our eyes, we have organs at the back of our eye. The organ is called the retina, and we have things called rods and cones that have little charged objects in them that are just like the pith ball, but they're tuned to sense the vibrations of those electron jumps. So in a visible light, the electrons are jumping. There's not little people in the light going, that'd be really cool. But the electrons are jumping. That's a vibration of a charge. That produces a little burst of light. In our eyes, we've got, in our rods and cones, the organ in our eyes, there's another charged object that wiggles in response, sends a nerve impulse to our brain. We see the light. Do you see the light, Kendall? Do you see the light? Excellent, good. That's my little, no, forget about it. Okay. So, that's what light is. Light is a wiggle in an electric field. And depending on how quick the wiggle is, we have different forms of light. And that's what we want to talk about next. So, what is light? No need to draw the pictures or anything like that. Right there. It is a wave of electric and magnetic fields. Now, I didn't talk to you about the magnetic field. I just talked to you about the electric field. If you continue on in physics, you will learn that electric fields are kind of linked together with magnetic fields. To be honest, I could have taken a magnet and wiggled it at a lot of frequencies per second. Same thing as the other. I'm looking for my magnet. Right here, I got my little magnet here, right? You could actually do it with a magnet as well. I still can't wiggle it fast enough, but a magnetic field and an electric field are very much related to each other. So, if we have a disturbance in the electric and magnetic field that exists in space, then we have light. All right. So what I want to talk about now is the electromagnetic spectrum. I do want you to, I want you to write this thing down. Yeah, isn't it terrible? I want you to write a line of some sort and put the frequencies. The size doesn't matter. The size of the space does not matter. And actually, I'm going to change a few things here, so I'll work with you here on this. So write down what the electromagnetic spectrum is. The type of electromagnetic wave depends on how fast the electric field wiggles. Let's start right down here, okay? And for all of, oh, I don't like all these. Let's get rid of these, all right? And let's call these radio waves. Just put radio down here, all right? So here's the way I want you to do this. Did you write down the first part? So, draw a line. Right there, right across your page. Okay? And down here, and up to here, and you can put 10 to the 4 on one end, and 1 on the other end. Put 10 to the 4 and 1. And this is wavelength in meters, is what you're writing. This is how long the wave is. That's one way in which we determine what type of light we're dealing with. So from 10 to the 4 meters up to 1 meter, think about that. 10 to the 4, that's a lot of meters. That's in the tens of thousands of meters. We have what are called radio waves. Now, in the next section, from 1, and in here I do want you to write 10 to the minus 2. Let's not write radar. These are microwaves. It's supposed to be one word, but that's okay. You get the idea. So from your 1 up to here, 10 to the minus 2, you have microwaves. It comes from the length of the wave, which is around 10 to the minus 3 to 10 to the minus 2, and the prefix that we use in science to describe something smaller than milli, right? So if you've got a millimeter, the next smaller thing is what we call a micrometer, and the size of their waves are in that length of micrometers, and hence they're called microwaves, okay? So they're named after the length of the wave, which is micrometers. 10 to the minus 4 up to 10 to the minus 6. Infrared rays, you could write that down as just IR. You might know that as IR, infrared. All right, infrared. So this says, Sammy's squinting back there, 10 to the negative 4 to 10 to the negative 6. So the waves are getting very tiny now, right? We're phenomenally small. Somebody's device is playing some music. It's exciting. So, don't worry about it. There was some music going on over there. In the very middle here is visible light, and I'm going to get you to expand this in a moment, but right now let's jump over the visible light. 10 to the negative 8, ultraviolet rays. What do you want to put here? You can put infrared or IR, infrared. What's the short form for ultraviolet? UV rays. What is UV rays? What are they responsible for? Why are UV rays? Yeah, it gives you a burn or a tan. We're going to watch some videos in a minute, and we're going to look at a little more detail what all these waves can do. Ultraviolet, 10 to the negative 8. Okay? We're getting to some really small waves. 10 to the negative 8 meters. That's phenomenally tiny. After UV, you can see there X-rays. 10 to the negative 10, 10 to the negative 12. X-rays are pretty self-explanatory. You go to the dentist, sometimes you get an X-ray. You break an arm, they give you an X-ray. Which one are we looking at here? 10 to the negative 10, 10 to the negative 12. And the shortest type of rays in which we have are called gamma rays. Now when you're done that little piece in the middle between the IR and the ultraviolet, expand it out, all right? Gamma rays, 10 to the negative 14, sorry. Microwaves, 10 to the negative 2. Okay? Expand out the visible light. And you know what? I'm not worried about the wavelength in nanometers, but nanometers are 10 to the negative 9 meters, so 400, 500, 600, 700. Let's not worry about it. But what we do want to do is put the colors. So I always remember the colors of the rainbow by a silly name. Have you heard this before? Roy G. Biv. Have you ever heard Roy G. Biv before? All right. So starting just above infrared is red, orange, yellow, green, blue, indigo, violet, and that's Roy G. Biv. You don't have to color it in. Just put Roy G. Biv in there. Roy G. Biv. Like it's a guy's name.
Oh.
Yeah. It's like supposed to be a guy's name. Roy G. Biv. I've never met Roy G. Biv, but I don't know. Red, sorry? What was the question? At 800? Yeah, it's very close to 800. Yes, it's very close to 800. The visible spectrum goes from wavelengths of about 400, and the easy way to memorize it is that the red end is about double. It's about 800 nanometers. So it's a complete doubling of the wavelength to get you from violet to red. And if you were to learn more about wave theory and frequencies, in music, when you double the frequency, it's called an octave. So that's an interesting little thing about light. We actually can only see about 1 octave spacing of light color, where in our ears we can hear all kinds of different octaves. We can hear a vast range of sounds, but we can only see 1 octave worth of light. Yeah. Okay, so there's our electromagnetic spectrum. Violet. Yep. No, it's violet. It's V. Okay? So now for the rest of the class, and this is where I'm going to stop the movie here in a moment. For the rest of the class, I am going to go over a little YouTube series of movies that I found, and it's out by NASA. It's actually pretty good. And we're going to watch each of them, and you're going to write down what type of radiation we're dealing with, what the wavelength is. I'm pretty sure it says it in the video. If not, we'll find it. It's not a big deal. I want you to listen for a source of the radiation. In other words, how is that particular type of radiation made? And then during the video, if you could come up with some applications or these maybe where it's used, et cetera, then that would be great. And after each video, we'll talk a little bit about what we saw, and we'll make sure that we've got each box filled in. All right? So you don't have to write this down. The only thing you have to write down, if you didn't, I had a page on here on the website that had all the boxes on it. So if you've got that printed off, you're filling it in. If you don't have it printed off, it's not a big deal. You're making a table with those headings, and you're just going to write on your page underneath there, all right? And for those of you who are not here I'm talking to the class who isn't here, as you watch the video, right, you're going to just go to that link, and then you're going to watch, and you're going to fill in the boxes. That's what you're going to do. So right now, as you're making the table, I'm going to stop the video, and we're going to get ready to do this, and those who are